Hi, my name is Pearson Rackley, and this is my video presentation on Lab 4, Circuits and Capacitors for Physics 2212. The object of this experiment was to observe the behavior of circuits with resistors in series and parallel, while also measuring the actual voltage and potential differences. To do this, we utilized the circuit construction kit and multimeters. We modeled the behavior of capacitors and ohmic resistors utilizing the circuit construction kit, the CCK, online, and we utilized multimeters to measure conventional current and potential differences. The key physics concept we utilized throughout this experiment included Ohm's law, which states that voltage is equal to resistance times current, the concept of capacitance, which states that capacitance is equal to charge divided by voltage. Next, we used the loop rule, which states that the total potential difference around the circuit will equal zero, which is drawn from the energy conservation principle. And lastly, we utilized the node rule, which states that current flowing in must equal current flowing out, given the current conservation principle. Two takeaways I have from this experiment was that the circuit construction kit proved to be very valuable for modeling circuits and capacitors, and I was able to visualize and calculate the key differences between the circuits in series and the circuits in parallel. In the first part of the lab, I explored charge conservation and energy conservation in a series circuit. I was able to predict the currents of I1 and I2 given I equals V divided by R. Given the values of V and R, I was able to calculate and predict that the value of I would be 0.02 amps. I was able to conclude that I1 and I2 would be equal given the closed system and therefore being able to utilize the loop rule. I provided my computer model on the bottom right hand of the screen and found that my prediction was correct and that the values of I1 and I2 would equal 0.02 amps. Next, I found that when the ammeter was inserted backwards, the values would read equal but negative what I found before. In the next step, I replaced the top ammeter with a voltmeter. By replacing it with a voltmeter, I expected that the ammeter reading would read 0 amps and the voltmeter reading would read 3 amps because the circuit was now open. The next step was to measure potential differences around the circuit. It's important to note that there was a constant current of 0.02 amps throughout the circuit. I found the values of AB to equal 3 volts, CD to equal negative 0.96, EF to equal negative 2.04 volts, and all other values to equal 0 volts. I was able to double check my work by confirming that the sum of all values would equal 0 given the loop rule. In the bottom right, I added the completed version of the potential versus position around the circuit, showing and labeling the various measured potential differences. Essentially, I found that the areas with the greatest change in voltages would be seen with areas in the graph with the steepest slopes. Next, I placed the ammeter in parallel to the 100 ohm resistor, and I saw that both ammeters read 0.06 amps. This makes sense because as the resistance increased, the current decreased, or as the resistance decreases, the current will increase. And because the second ammeter is in the path, it increases the resistance of the path. Here I show my calculations for resistance using Ohm's law, which states that the resistance will be delta V divided by I. For the first resistor, I found the resistance to be 48 ohms. For the second resistor, I found it to be 102 ohms. And then R of the wire would be 0 ohms, and R of the ammeter would also be 0 ohms. Here I worked with an RC unit and utilized changed resistor values to observe how a light bulb works when a battery is connected in series in RC circuit compared to being connected in series to a charged capacitor. Both were read on a 10 ohm bulb and a 20 ohm bulb. I found that in both cases the bulb lights up very brightly, then slowly dims over time as it moved towards 0. And I found that it took less time for a capacitor to charge than it did to discharge. And overall, I found that it took longer for both charging and discharging for the 20 ohm bulbs. Finally, I wanted to observe the time-dependent voltage across a discharging capacitor. To do this, I measured the potential difference and took the natural log of the current voltage divided by the initial voltage, which is equal to negative T over RC, which is the time constant. On the right, you can see that the line is fairly linear in the negative direction. I found the slope to be negative 0.014 0.466x. I was then able to find the time constant by dividing -1 by that slope and found that -1 divided by -0.01466 equals 6.82 seconds. To wrap up this experiment, I ended with a few reflection questions. In response to the first reflection question, I found that the real ammeter was not perfect and has its own resistance. Because of this, there were different calculated current and potential differences. Next, I found that although the model shows that the capacitor would be charged instantaneously, real capacitors would take much longer because of their resistance, which slows down the process overall.